This clip is part of the Neuromuscular Junction series. We have already looked at neuromuscular junction excitation part where the neuron is exciting the muscle, but now this is part 2 in which the muscle is actually going to start to contract. So this clip is going to focus on how our muscles contract, the molecular events that result in muscle contraction. So what is muscle contraction? Well, contraction is the step in which a muscle fiber is going to develop tension. And in this case, the muscle may also shorten. And so when we say that the muscle shortens, we're actually referring to the smallest functional unit, that is the sarcomere. And we've looked at this anatomy in a previous video, but today we're going to understand that the sarcomere overall will shorten in length during muscle contraction. And this occurs because of interactions that occur between the myosin and the actin filaments. So let's go ahead and zoom in on these structures in order to understand how they work together in order to complete muscle or result in muscle contraction. So let's begin. Well, step number 1 is that actin and myosin don't really interact quite yet. There are several different factors that need to come into play in order to allow myosin and actin to communicate and then start sliding across one another. This is going to result in contraction, and this is why we call this mechanism the sliding filament theory, because it is thought that actin and myosin are going to slide against each other in order to result in sarcomere shortening. So what's the first thing that happens? Let's go ahead and start by labeling our important players. As you can see, we have myosin and we have myosin heads, and these are what we're going to be focusing on because this myosin head is what's going to interact with actin. Now on actin, what you also see is that actin has what we call a myosin binding site. And this site has to be exposed in order for myosin to bind to it. And we'll talk about this mechanism a little bit later today. But let's first focus on myosin itself. So myosin itself, first, it has to be energized. It has to be ready to be able to interact with actin. And so, first of all, myosin heads have what we call the ability to hydrolyze ATP. And so they are able to convert or hydrolyze ATP into ADP and P phosphate. And so by doing so, when an ATP molecule binds to the head, it can then break it down, the head can itself break it down into ADP and P. So this is step number 1 that we call hydrolysis of ATP. So after this hydrolysis step is complete, now the myosin head is attached to ADP and phosphate. And this is what results in the energizing of the myosin head. So now it is ready to start its bond with actin. So step number 1. Moving on to step number 2, as you can see, now we have the ADP and the P, and this is what allows the myosin head to bind to actin, specifically at the myosin binding site. And this is what we call cross-bridge formation. So cross-bridge formation has taken place in step number 2, and this is basically the binding of myosin head to actin. Now let's move on. So step number 3, right around here, what you'll notice is that these arrows are indicating a specific movement. And so when we say sliding filament theory, it is referring to this movement because what happens is that the myosin head is now able to bend and move actin with it. And so when it bends, this is what we call the power stroke. And during this time, as the power stroke is occurring, well, ADP and phosphate are also being released. And so after the cross-bridge formation, ADP and phosphate will be released off of the head of myosin, and the power stroke can also take place. Okay, so power stroke occurs, and this is defined as the movement or the sliding of actin over myosin. Okay, and then we can also add ADP and P released from the myosin head. This action right here, if we refer back to our sarcomere, when these myosin heads are bound to actin, and then they're going to go ahead with the power stroke, this is what causes the movement of the sarcomere towards the middle or M line, and this is what results in sarcomere shortening. The final step of the sliding filament theory is pretty much the release of myosin from actin, and this only occurs in the presence of ATP. So, binding of an ATP molecule to myosin is going to allow myosin to detach from actin. If ATP is not present, then myosin is stuck to actin and cannot detach. So it's the presence of ATP that's really important and necessary in order to break this attachment. And this cycle goes on and on and on throughout the muscle contraction. So now that you're familiar with the sliding filament theory, let's backtrack a little bit and re-examine the initial step. I mentioned previously that the myosin binding sites on actin have to be free and exposed in order for myosin to be able to bind to actin. But that is not the case in a muscle at rest. At rest, a muscle kind of looks like this. If you look at actin, you're going to notice that we have tropomyosin, a protein, just kind of blocking the myosin binding sites on actin. And so that's a problem because myosin cannot bind to it. So here is where calcium comes into play. So if you remember from a previous video when we were talking about the neuromuscular junction and how the neuron excites the muscle, well, the first event that occurs is calcium is released in the muscle from the sarcoplasmic reticulum where it is stored. And so this step is very, very crucial in order to allow muscle contraction to occur. Because when calcium is released from the sarcoplasmic reticulum, they can now bind to troponin. And troponin is another protein also attached to tropomyosin. And so when calcium can come in and bind to troponin, this is a really important step because it's going to cause a conformational shift. So troponin will shift, it's going to move a little bit, change shape, and this shape change is going to displace tropomyosin out of the way. And this is going to expose the myosin binding sites for myosin to bind to actin. So let's summarize. So calcium is released from the sarcoplasmic reticulum and it can bind troponin. The next step is that troponin will change shape, and this shape change is going to allow tropomyosin to be displaced. So moves tropomyosin out of the way. So what's going to result now is that the myosin binding sites on actin are going to be exposed. And what's going to result? Well, this is going to allow the sliding filament theory to occur because the end result is myosin can now bind actin. So here's where the process will start. The only requirement is that myosin has to hydrolyze that ATP into ADP and phosphate and then move through the steps as we have highlighted them earlier in this clip.